Last time we found this expression for a limit based on the secant line approximation of an exponential function's derivative, or slope. That limit is a scale factor whose value depends on the base b. Ideally, if we want to get a scale factor of 1 exactly, the base b must be a special number. That number we call e. If you missed the last lesson and want to catch up on the details, please do so now before continuing with this lesson. As just mentioned, that limit is a scale factor whose value depends on choice of base b. Using notation consistent with what we've already seen, the general form of an exponential function is a scale factor a times base b raised to the x. The scale factor a is boxed in red. So let's now try to make that scale factor equal to 1. To do that, we will set the limit equal to 1. I'm going to pull out the expression inside the brackets to manipulate the algebra. Then at the end, we will let h go to 0. The second line is the same as the first, except I got rid of the limit notation for the time being. In the third line, I multiplied both sides by 2h. Then in the fourth line, I multiplied every term by b to the h. Pay attention to the green and blue underlines. In the next slide, I correlate those to the laws of exponents I used to make that simplification. In the last line, I move everything to the left-hand side and set the right-hand side equal to 0. Multiplying exponents with the same base follows the rule boxed in red. I use the laws boxed in green and blue to make the simplifications seen on the last slide. Go back if you need to see how I made that leap. If you're still confused, don't hesitate to ask a question in the comment section below. You should remember the quadratic formula from high school algebra. I've also done a lesson on this if you need a refresher. This is what we're going to use next. The first line is the result we got from a couple slides back. Notice that we can make this fit the quadratic formula with coefficients a equals 1, b equals negative 2h, c equals negative 1, and x equals b to the h. Plug those in and simplify. You should get the result seen in the last line. Notice the h plus square root of h squared plus 1. Since h is in the limit going to 0, it turns out we can simplify this expression a bit. Here I have made a spreadsheet with a bunch of values of h. Each row gets a little bit closer to 0. Notice by the last row that h plus the square root of h squared plus 1 is really close to h plus 1. We are going to employ that simplification to our advantage. By the way, please make your own spreadsheet if you need to verify these values for yourself. Now we bring back the limit and let h go to 0. As we just said, we are going to replace h plus the square root of h squared plus 1 with h plus 1. That means when we use the quadratic formula to solve for b to the h, we get b to the h equals 1 plus h. Remember from our laws of exponents that b to the 1 over n is the same thing as the nth root of b. We are going to use that notation in the next slide. In the first line, the left-hand side equals b to the h. To get b by itself, we must take the hth root of both sides. That is seen as 1 over h on the right-hand side in the second line. Finally, substitute n equal to 1 over h. That leaves us with b equals 1 plus 1 over n quantity to the nth power, as seen in the last line. That looks familiar from our lesson on compound interest. Here's a quick reminder from that lesson. The result boxed in red is exactly what we just derived. So it appears there is a connection between continuously compounded interest and the slope of an exponential function. The common factor between these two is the number e. Another reminder from the lesson on compound interest. If we plug in the value for n into the previous formula, we get the number in the rightmost column. In that lesson, we started with $1,000, so divide every number by 1,000, and it looks very close to e. 2.718 is quite close to the value of 2.75 we got in the last lesson. Now we are going to show how to perform these computations. We can plug the values n in the left column into 1 plus 1 over n, quantity raised to the nth power. Notice as n gets very large, the value in the right column approaches a number around 2.718. If you have a scientific calculator, the easiest way to crunch these numbers is by using the button boxed in red, y to the x. That seems simple enough, but it doesn't do justice to the underlying algorithms. I would like to explore that algorithmic side a little bit more. Remember that exponentiation is repeated multiplication. So for n equals 10, we can multiply 1.1 by itself 9 times. A little tedious, but not too bad. The number at the bottom of the screen is the one we saw in the table. Go ahead and verify this number for yourself. Now how about n equals 100? The approach of repeated multiplication entails 1.01 times itself 99 times. That is very tedious, but it will give us the number at the bottom of the screen. Is there a better way to do this? Why, yes, there is. We can use our laws of exponents to greatly simplify things. Notice that each time we are squaring the answer from the previous line. This is one multiplication per line. 100 is equal to 64 plus 32 plus 4. So we can multiply those exponents to get 1.01 raised to the 100th power. This entails only 8 multiplications and gives us the same number in the end. Much simpler. For n equals 1000, I'm not even going to show repeated multiplication. It wouldn't fit on the screen. Cutting right to the chase, we begin with these multiplications up to 1.001 raised to the 1024. Take note of the values underlined in red, green, and blue. We will see them again in the next slide. 1000 is equal to 1024 minus 16 minus 8. Using our laws of exponents, we can plug the 3 values from the previous screen into this expression to get the number at the bottom of the screen. So instead of 999 multiplications, we have 10 multiplications and 2 divisions. Go ahead and verify these numbers for yourself. You may have noticed there's another way to get the exponent to 1000. That would entail 11 multiplications and 1 division. If you know the answer, please tell us in the comment section below. At any rate, we can keep going with this approach. Try for yourself and compare your answers to mine seen here in this table. It should take about 24 multiplications or divisions for n equals 1 million. That being said, notice that only gives us 5 digits of accuracy past the decimal. It turns out there are more efficient ways to compute e. That is what we will explore in the next lesson. Before we go, take a look at this graph. I've plotted the values from the previous table. The flatness shows that the limit is converging around 2.718. That is consistent with what we have seen thus far. Thanks for watching this lesson. I hope you learned something new today. Please show your support by liking, commenting, subscribing, or sharing this with a friend. I greatly appreciate it and look forward to seeing you again.